And let me introduce you. So it's a pleasure to have here today Professor Segreto. Professor Segreto got his PhD in physics in 2006 at the Università degli Studi dell'Aquila in Italy. And then he held many faculty and research positions at Università degli Studi di Roma Tor Vergata, Università di Studi dell'Aquila, and Laboratorio Nazionale del Gran Sasso. And since 2015, he has been a faculty at the Gleb Wataghin Physics Institute in Campinas at UNICAMP. And today he's going to talk to us about the mysterious neutrinos and the Brazilian ARAPUCA to catch them. Professor Segreto, thank you very much for accepting our invitation, and the microphone is yours.
Thank you, George. It's really a pleasure to give this seminar. I will give a brief overview of the history of neutrinos, the discovery, the hypothesis, and what we are looking now. I will focus on the experiment I'm working in this moment, that is the DUNE experiment, which is having a significant support in Brazil. In fact, Brazil is among the most important contributors of this experiment in terms of financial terms and also in terms of technology, because this ARAPUCA is part of this experiment. Is probably the first time that Brazil owns a technology which goes inside one of the most important experiments in the world. It will be an experiment at the level of LHC experiment at CERN. And there are possibilities, I will talk at the end of the talk, for students. We are going into the construction phase of the detector, and it's a very interesting phase, and then we will go into data taking. So is an exciting moment. But we'll say more toward the second part of the talk. Let's start with neutrinos. Neutrinos are the most abundant particles of the universe if we neglect photons, and are one of the key elements that could explain why our universe exists in the form that we know today. And this, in fact, is one of the main topics of studies of the next generation of neutrino experiment, both DUNE and both Ipercamiocande in Japan. But the neutrino was discovered, the existence of neutrino was, the hypothesis of the existence of neutrinos is relatively recent. It dates back to 1930. And we were able to detect neutrinos just only 26 years after the hypothesis of the existence of neutrino, 1956. And the neutrinos still hide some secret that we want to discover. So they are, for this reason, I'm calling that the mysterious neutrinos, because there are things that we probably understand with this new generation of experiment. Neutrinos are very abundant in every place in our art and the place of the universe. Think that about 100 billions of neutrinos cross each square centimeter of our body in each second. These are neutrinos produced by the most intense source that is nearby to us, that is the sun. So it is an extremely high flux of neutrinos crossing us in every moment. But they not only cross our body, they cross the Earth, the entire Earth without problems, and the entire universe without being disturbed during their propagation. For this reason, neutrinos are called also the ghost particles, because they exist, but it's very difficult to have signal of their existence. So it's very difficult to catch them. Now I would like to go back in time. As I told you before, the story of neutrino is about 1 century old. So I want to make a brief historic overview of the hypothesis of neutrino, how we're discovered and where we are now. The discovery of radioactivity dates back to the end of the 19th century. As we know, Becquerel discovered the radioactivity of uranium using photographic emission. Also, in this case, there are stories that it was not really the discoverer, but was a photographer that noticed that small minerals containing uranium had the capability of darkening photographic emulsions. But clearly, it didn't have the background to make some kind of physical hypothesis of the reason of this. Later, Marie and Pierre Curie discovered the radioactivity in the thorium and in other elements, and then discovered also new elements like the polonium that was named after the Marie Curie, since she was a Polish girl, Polish woman, and radium. Toward the end, in 1899, the end of 19th century, Rutherford was able to make a classification of these radioactive emissions. He distinguished between alpha and beta emission, depending how much the products of this decays were able to penetrate into aluminum slab. And later, there was a discovery of another type of emission that was even more penetrant than alpha beta, beta emission. That was then he named this kind of emission as gamma. We know today that the alpha emission in a nucleus correspond to the production of a helium nucleus, which is emitted with a certain energy. For example, here I'm representing the alpha emission from a uranium nucleus. That was the one which triggered the discovery of the radioactivity from Becquerel. So we know that uranium 238 decays to a thorium 234, emitting an alpha particles. These are two states with the fixed energy. It is a two-body decay, and so the alpha particles carries out a fixed amount of energy. So if we go and measure the spectrum of energy of the helium nucleus, we obtain more or less a delta function smeared by statistical effect, by detection effect, and so on. But it's something which we can understand. Also at the time where radioactivity was started to be studied, was easily understandable. So there's a two-body decay, so the product of decay is a fixed energy. But the beta decay put in crisis all the system of the physics at that time. So the conservation of energy is okay in this case. Because in this case, the beta emission that were identified as being electrons had a continuous spectrum. So the question is the following: if the decay is the same, two-body decay, how can the product of the decay have a continuous spectrum? There is something which is not working. Is it possible that energy is not conserved in this kind of decay? And this is a question that was seriously taken into consideration by physics in that time, at the beginning of 20th century, in 1920 up to 1930 and so on. And there was a very famous letter of Wolfgang Pauli addressed to the people participating to this famous conference in Zurich, where he made the hypothesis of the system of this ghost particle. He made the hypothesis that the beta decay was not a two-body decay, but a three-body decay, where one particle was not detectable. So that the sum of the energy of electron and this other particle was constant, so that the energy was conserved. And he wrote, if you are not familiar with German, he wrote in this letter that he did something very bad today, proposing the existence of a particle which cannot be detected. And it's something that the theoretical physics should never do. But in this case, as sometimes happens, one should try to choose the thing which is less worse. So Wolfgang Pauli decided that was, according to his perception, was better to preserve the energy, the principle of energy conservation, despite hypothesizing the existence of a ghost particle. So this ghost particle was named Neutrino by Enrico Fermi. Was an Italian physicist working in Rome at that period, at that time. And in 1934, he made this hypothesis of the beta decay in parallel with the electromagnetic, with the electromagnetic disexcitation of the atoms. So he made the hypothesis that the neutrons decays into protons with emission of an electron and the particle which is an antineutrino. So that the antineutrino goes undetected. So we detect just the electron, and the sum of the two gives the difference in energy of the two between the neutron and the protons, and the energy conservation is safe. But it took a lot of time to detect neutrinos, because as I said in the introduction of this talk, neutrinos are very elusive particles, since they interact very rarely with matter. And they were detected, were discovered in 1956. That means 26 years later, the hypothesis of Pauli, with the famous experiment of Reines and Cohen, that put a neutrino detector nearby to detected solar neutrinos. Then, in 1962, Lederman, Schwarz, and Steinberg discovered a neutrino which was identified to be different from the neutrino discovered by Reines and Cohen. That was named neutrino mu. And much later, just 24 years ago, in 2000, a third type of neutrino was discovered, the neutrino tau. The first neutrino which was discovered by Reines and Cohen is the neutrino E. So the current model, standard model of particle physics, tell us that we have three types of neutrino. Each one which is associated with one of the three leptons, electron, muon, and tau. So we have a neutrino electron, neutrino mu, and neutrino tau, and their antineutrinos. They don't have electric charge, and they interact just by weak interaction. This explains why it is so difficult to detect them. They were hypothesized that they are without mass. This is not exactly true, because now we know through a series of very famous experiment, neutrinos have a mass. small one that we are not able to measure, but they have mass. This is something which opens some questions for the standard model, since the standard model does not predict neutrino mass. So the existence of the mass of neutrino is something which opens a window over new physics with respect to the standard model of particle physics. And along the years, we discovered many sources of neutrinos. As the first one, the most abundant that I have already touched before, is the sun, which emits neutrinos with low energy between 0.1 and 14 megaelectron volt. Then there are the atmospheric neutrinos, which are produced by an interaction of cosmic rays with the atmosphere, which have energy between above 100 MeV. It can be very energetic. There are neutrinos coming from the radioactive decay in the heart, geoneutrinos, which the type decays of radioactive element in the core of the Earth. With this are called geoneutrino and have energy of the order of few MeV. Abundant neutrino emitters are the nuclear reactors with energy of few MeV. They are neutrinos which are remnant from the Big Bang with very small energy, which are almost impossible to detect. And then there is a source which is used today with more frequency in order to study with precision the property of neutrino. These are the neutrinos produced in accelerators, and are the ones which will be used also by the experiment I will talk later, the DUNE experiment. And then another interesting but unpredictable source of neutrino are the supernova. When a star with a mass above a certain limit consumes all its nuclear fuel, hydrogen, helium, and so on, it implodes and release a huge amount of energy. The vast majority, more than 99% of the energy is released into neutrinos. Even if they are very bright, the fraction of energy which goes into photons is negligible with respect to the energy which goes in neutrinos. So if one supernova explodes in our galaxy, with the detectors we have on the Earth, we will observe a very intense flux of detected neutrinos. To have an idea, in the modern experiment, we expect to detect 3,000 neutrinos in a time of 10 seconds, while the number of neutrinos detected coming from the sun is the order of 100 neutrino per day. So it will be a very bright signal that can give a lot of information about how a star ends its life, and also about neutrino properties and so on. So it's a very hot topic of studies today, nowadays. As I told at the beginning, neutrino are a continuous source of surprises. It started from the beginning. People, when first neutrinos were detected from the sun, started doing experiments to catch as much neutrino as possible to start making quantitative studies. Neutrino in the sun are produced to this chain of reaction that is very well known. And so the flux of neutrino from the sun is predictable with great precision. An interesting fact with respect to the solar neutrino is that they are produced in the core of the sun, and they leave the core of the sun instantaneously. So, and they take 8 minutes to reach the Earth. So neutrinos brings information about the status of the core of the sun instantaneously. This is not true for the photons, because photons which are produced in the core of the sun takes a lot of time to reach the surface, about 10,000 years, because they scatter every time. So with charged particles, so they take a long time to reach the surface of the sun. So the best way to monitor the status of the core of our star is looking for neutrinos. So what happens? In the 60s, Davis made a very famous experiment trying to detect neutrino from the sun. And what he noticed was that the number of detected neutrino was much less than expected. Expected from estimation made with this standard solar model that was very well known and gave very precise prediction in other things, in terms of luminosity, in terms of all the other quantities predictable within this model are very precisely predicted, with the exception of neutrino which arrive to the Earth. The fraction of missing neutrino is pretty big. Davis noticed a rate of detection was less, 1/2 of the value that expected. And so at that time, there was a long discussion about the accuracy of this model, of the accuracy of the experiment of Davis, and so on, because it was something which was pretty strange. But in the following years, so starting from the 90s, with the experiment SAGE, Galaxy, GNO, which use a particular reaction of gallium with the neutrino produced from the sun, which are electron neutrinos. These are very sophisticated experiments which make the count of the germanium atom in tons of liquid containing gallium. So one of these was at Gran Sasso, so I know pretty well because I was there. And so also in that cases, they measured the significant lower rate of neutrino-electron interaction from the sun with respect to the expected value. And the following experiment in the following years confirmed strongly this evidence. So neutrino are missing. So this is a fact. In parallel with the anomaly of the solar neutrino, what was also discovered was the anomaly of the atmospheric neutrinos. As I told when I was illustrating the sources of neutrino, I mentioned the atmospheric neutrinos. Earth is continually, the atmosphere of our Earth is continually bombarded by cosmic rays, which are substantially protons. This interaction produce pions and some kaons. The charged pions decay producing muon and neutrinos through these two very well-known decays. Pions in muon plus muon neutrinos. A muon decay into an electron or positron, antineutrino electron, neutrino muon, or mu plus decays into a positron, neutrino electron, and antineutrino muon. So from each decay chain, one obtains two muon neutrino and one electron neutrino. So if I build a detector which is able to detect neutrino, muon neutrino, and electron neutrino, I would expect an average value of the ratio of the two around 2 muon neutrino for 1 electron neutrino. Also in this case, this prediction is wrong because the ratio which is measured is something around 1. So also in this case, there is a large fraction of neutrino muon which is missing, or there is an increased production of neutrino electrons. So something unexplained is going on, and this is anticipated is related to the fact that neutrino have mass. So this is just a joke. This is the front of the lab where I stay now. where we have the Enrico Fermi and Cesar Lattes, which are respectively the discoverer, let's say, even if it was not granted with the Nobel Prize, or the pioneer, and one of the most relevant physicists in neutrino physics, Enrico Fermi, and which are linked by the decay of the pile. So this is just a joke. And so now, what is the how do we resolve this issue? Also, in this case, there was a very long discussion among physicists, and what was realized is that neutrinos oscillate. That is, the three neutrinos that we know, neutrino electron, neutrino muon, neutrino tau, have a small mass, which is not foreseen by the standard model of particle physics. And this circumstance allows the neutrino to oscillate. What does it mean? That is, a neutrino which is produced as a muonic neutrinos can transform into neutrino tau along its propagation. Or a neutrino which is producing as a neutrino electron, for example, from the sun, can transform along its path to the Earth in a neutrino muon. So the missing neutrinos, which are of the solar neutrino experiment, are not really missing. They're just transforming into neutrino muon, because the experimental Davis and all the other experiments, many of the other experiments detecting solar neutrino were not able to detect muon neutrino. So if a neutrino electron transforms a neutrino muon, what happens is that we miss a fraction of the solar neutrinos. There is more recent experiment by Professor Arthur MacDonald, who got the Nobel Prize in 2015, who was able to detect simultaneously the three types of neutrinos, nu, mu, tau, from in the range of energy of the solar neutrinos. And he was able to demonstrate that the sum of the three neutrinos is constant, despite that there is a fraction of neutrino muon which is produced by the oscillation of the neutrino electrons. And so the same happens for the atmospheric neutrino. There are neutrino muon which are oscillating to neutrino tau, so the ratio of neutrino electron to neutrino muon does not respect what we are expecting. This is, I will not go too much into details, this is an effect, a macroscopic effect of quantum mechanics. Is an effect of quantum interference between among physics autostates of the neutrinos. And briefly, what happens is that in the accelerators, just to simplify the problem, we produce generally neutrino muon, and we put a detector at a certain distance. If the distance is short, then we will see what means for short. Nothing happens substantially. We produce neutrino muon and we detect neutrino muon. If we increase the distance a certain level, strange things happen. This neutrino that we produce as a neutrino muon can be detected, for example, as a neutrino E. This is the neutrino oscillation. Or more precisely, there is a probability that a neutrino which is produced as a neutrino muon is detected as, for example, a neutrino tau, which is a probability which depends on the distance where I put my detector, on the energy of the neutrino, and on some intrinsic parameter. For example, like this angle theta, which is a mixing, we call mixing angle, it's a characteristic parameter of the neutrino oscillation. So the oscillation probability, the probability that neutrino mu is detected as a neutrino tau as a function of the distance and of the energy neutrino is this one. C square of 2 theta times C square of 1.27 delta M square, which is the difference in mass between neutrino mu and neutrino tau, expressed in electron volt square, the distance traveled by the neutrino and the energy of the neutrino. And so you see that the distance that the neutrino needs to travel, the distance at which we need to put our detector is several hundreds of kilometers to observe the effect of appearance or disappearance of neutrino. And in fact, these are the ranges where the detectors are installed from the source, order of several hundreds of kilometers. So a very complicated experiment. Imagine you need to create a neutrino beam in a place and then detect them 1,000 kilometers far away. Considering neutrino is a neutral particle, so you typically are not able to focus them very well. So if you produce, at the best of our technology, neutrino in a place, when they travel 1,000 kilometers, the beam of neutrino is tens of kilometers large. So you need to beam a very intense neutrino flux, neutrino beam, in order to detect something which makes sense after hundreds of kilometers or thousands of kilometers. And an interesting aspect that neutrinos, that we think neutrino will allow us to explore is the CP violation in the leptonic sector. That means the CP symmetry is in physics is the operation which transforms, for example, particle into antiparticle, so neutrino into antineutrino. If the nature were perfectly symmetric, particle and antiparticle should behave exactly the same way. This probably is not the case. This cannot be the case, because if it were exactly like this, if matter and antimatter were exactly one the specular of the other, the universe as we know could not exist. Imagine a Big Bang where matter and antimatter are created in the same quantities. So we have the same amount of positron, the same amount of electrons, the same amount of matter, the same amount of antimatter. So when the universe cools down, so that the matter and antimatter can get in contact, can annihilate, all the antimatter will annihilate antimatter. So we know that when a particle meets an antiparticle, what is produced is a flash of light. So if we have the same amount of matter and same amount of antimatter at the beginning of the universe, after some time, they will recombine. So, and each particle of matter will recombine with a particle of antimatter, produce a flash of light. So the universe, after the Big Bang, should end up just in a flash of light. In the case that matter and antimatter were perfectly symmetrical. Clearly, we are the proof that this is not the case. So there is something which is not exactly symmetrical. And why this happened is not clear yet. This is the object of this sophisticated experiment on neutrino and also on other particles. But we believe that neutrino can be a good bet to understand this asymmetry in the nature and this unbalance that can have produced this unbalance between matter and antimatter after the Big Bang. The process that, I mean, if you want to make some, if you study more about this, the process which should cause this imbalance is called the leptogenesis, which is linked to the baryogenesis. which are the two processes which are supposed to create the imbalance between leptons and antileptons, baryons and antibaryons in the early universe. There are a lot of neutrino experiments today with significant participation from Brazilian group. I listed the most relevant one, the DUNE experiment, that I will say something more later, that will study the CP evaluation neutrino sector, leptonic sector, supernova neutrino, studies also on stability of the nuclear matter of the protons, SBND, which is an experiment in the US about the hypothesis of the existence of fourth neutrino, that is called stereo neutrinos. A small experiment like Lariat, another experiment of Fermilab, which is NOVA, Juno, which is an experiment which will be in China with the reactor neutrino, Ice Cube, that is an experiment in the South Pole, Connie, that is an experiment which is in Angra, and Angra, which is another experiment in Angra with which is trying to detect neutrino from the reactor, from the Brazilian nuclear reactor. I will go in some details about DUNE, since it's the experiment where the Brazilian group has leading roles. DUNE is a very big collaboration, which involves about 1,500 researchers from 200 institutions from more than 25 countries. The physics goal of the experiment are very ambitious and are listed here. As I mentioned before, we want to investigate the possibility of violation of the CP symmetry in the leptonic sector. We will use a beam of neutrino, a beam of antineutrino, and we will see if the event that we detect prove the violation of the CP symmetry in the leptonic sector. We want to measure the mass hierarchy of neutrinos because not only we don't know what is the absolute value of the neutrino mass, but we also don't know what is the ordering of the mass of the neutrinos, which is the lightest one and which is the heaviest one. And then we want to make precision measurement of the parameters with determine this process of oscillation. In parallel, we will be able to make studies of the eventual neutrinos produced by supernova explosion and studies of the something which is the Graal of physics beyond standard model, which is the chi of the protons, which is predicted by several models behind the standard model. So it's something which is being searched for by many experiments. Just a bit more in the detail. This is a sketch of how the experiment will be. As I told you before, we will have a neutrino beam which is produced in the most important laboratory in the United States, which is the Fermilab, which is entitled to Enrico Fermi that I mentioned before, because after he was Italian, but during the war he left Italy and he moved to the US in Chicago, and after him the most important laboratory of the US is been named Fermi National Laboratory, entitled to this great physicist. So there is a particular proton accelerator which impinges protons on a target. The target produces charged particles, but it is the same process that happens for the cosmic ray. Protons produce pions. Pion in the case produce muon neutrinos. And so the muon neutrinos, the pions are focused in order to that the neutrinos, which are the product of their decay, are more or less focused. But as I said before, they are charged particles, so there is some physical limit in the focuses of neutrino. So they are propagated from 1,300 kilometers and are detected by underground detectors, which are installed in the South Dakota, in some underground laboratory in South Dakota, which is called the SURF, Stanford Underground Research Facility. And the laboratory is 1.5 kilometers in underground. We call the cavern. The cavern are finished, and now we are going toward the installation of the detector. These detectors are made of in 4 modules. Each module contains more or less 15,000 tons of liquid argon. Argon is a noble gas, which is liquid at cryogenic temperature, around 90 Kelvin. So is, as you understand, a very big enterprise. So this is a sketch of the experimental hall with the caverns, with the cryostat, and so on. Each one containing 17,000 tons of liquid argon. Why we use liquid argon? Because the detectors are able to make picture of the interaction of the neutrino. This technique is called the liquid argon time projection chamber. There is a volume of liquid argon which is immersed into an electric field which is produced between a cathode plane, which is a metallic plane, and an anodic plane which is made of wires. And we have typically 3 anodic planes. Each plane is able to produce a bidimensional representation of the event. So you see exactly as if it was a picture of the event. Combining the 3 bidimensional view that you have from the 3 planes, you have a 3-dimensional representation of the event. These are examples of interaction of neutrinos in other experiments. And this is an image of the prototype of DUNE that we installed at CERN, where you can see the 3-dimensional reconstruction, in this case of cosmic ray, since proton is installed in surface, crossing the detector. In combination with with this 3-dimensional representation of the event, which is possible thanks to the collection of the ionization charge, which is produced. Let me go back to the schematic. So imagine that the neutrino interacts here. The neutrino as neutral, so are not visible. They don't produce ionization charge. But the interaction produces charged particles. Charged particles propagate inside the liquid argon and ionize the medium. So the electric field separates this charge. So we detect the electrons go toward the anode that are drifted with the same geometry of the original, following the same geometry of the track that produced them. So the detection of the charge gives us the 3-dimensional representation of the event. In combination with the production of the charge, there is another channel, the production of light. Charged particles propagated in liquid argon produce flashes of light. This flash of light gives a lot of information about the energy of the particle, the type of the particle, and so on. So it's something which is very important to detect. The system which is used in the DUNE experiment is based on an idea which was proposed by us here in Campinas, and which is called the ARAPUCA. The ARAPUCA, as you well know, is a trap for birds, but we use the name because we are trapping photons instead of birds. This is something you can find a lot of information on the web. There is also divulgative material, so you can have you can find whatever you want about it. But the principle is very simple. So the scintillation light, which is in the vacuum ultraviolet at 120 nanometers, enters, is converted on a thin film of this material, Peter-phenil, which absorbs this light compared to 350 nanometers. Then there is a filter, an optical filter, which is a dichroic filter that is transparent below a certain cutoff, which is 400 nanometer, and reflective above this cutoff. So the converted photons goes inside this box. This is a reflective box. Are converted again to another wavelength of 430 nanometers, where the filters became reflective, and so they start reflecting inside this box until they are detected by this active photosensor, which are called silicon photomultipliers. So the idea is that the photon enters, are not able to escape, and so bunging inside this reflective box at a certain moment are detected by the sensor, light sensor, the silicon pair. The technology is being demonstrated in the prototype of DUNE, which is called Proto-DUNE, already in 2017, and since then we built a big team working on the development of the ARAPUCA in DUNE. These are the ARAPUCA, which are installed behind the wires of the time projection chamber that I showed you before the wires that detected the charge, and here you see Anna Melia, which is my wife, that now is at UNICAMP, and me during the installation of the modules at CERN. So some closer view. Let me skip. So now this ARAPUCA is very popular and is collected the interest of many other countries. And so there is a big consortium that is working on developing ARAPUCA, and the construction. Now we are going into the phase of construction. So there are several Brazilian groups, other group from Latin America, Colombia, Paraguay, and Peru, group from the UK, Czech Republic, United States, mainly from the United States, several Italian groups, and several groups from Spain. So this idea that was proposed, that was tested for the first time here at UNICAMP in the Sirius laboratory, grow exponentially. So now we have about 50 institutions which are spread all over the world, with more than 300 researchers, which have been working now since several years in this kind of detector. So this was my last slide, but I want to conclude saying that we are entering into a very important phase of this project, the project of DUNE, in particular of the project of the ARAPUCA. We are going into the construction. And so there are several opportunities for working on the ARAPUCA at UNICAMP and the university which are associated with us. We have a strong program of interchange with Fermilab. We typically send 4 or 5 students per year at Fermilab to spend a few months there to work not only on the DUNE but also on the SBND and the other experiment where we collaborate. So there is plenty of chance of making experience, which can be important then for the continuation of the career in physics. So if you are interested, if you think that this field of research can be something that you like, you can get in contact with me, and we can have a conversation about this topic. So, thank you.
Professor Segreto, thank you very much for this very, very nice talk. Very exciting. It's we as Brazilians, we feel very proud to be leading this research. So very nice. And we are open to questions. So if there are any questions, please either write them in the chat or open your microphone and ask the questions directly. I have a couple of questions. So I am, being a condensed matter physicist, I know nothing about the standard model. So I had the impression at some point that you said that the standard model does not predict the existence of neutrinos, but after that, it doesn't predict the mass of neutrinos.
The mass,
right?
Right.
The mass,
right.
okay. Predict the existence, but if they exist, they shouldn't have mass, right?
Right. Yes,
And
that's correct.
how accurate is the measurement of the mass of the neutrino? Can we really say that the neutrino has mass, or this is still debatable?
We can say for sure that it is a mass, because otherwise this mechanism of oscillation could not happen, because the probability of oscillation depends on the difference square of the mass of neutrinos. So if neutrinos do not have mass, they cannot oscillate. So this is sure, but the mass is so thin, so small that we are not able to measure it. And this experiment of an oscillation can measure just the difference in mass of the neutrinos. We need other experiment to measure the mass, the absolute mass of the neutrino. This is done typically with experiment with beta decay, or double beta decay without neutrinos, which is another topic which is super interesting, but well, would need another hour to talk about, or estimation come from cosmology, because the mass of the neutrino can have an impact on the structure of the universe. So they can put some limits on the mass of the neutrinos. Probably will take 10 to 20 years to have an estimation of the mass of the neutrino. While the difference of the masses will be measured precisely by the next generation of experiment of oscillation that are DUNE and the Japanese one, which is the Perkamo-Kamokande. So DUNE will start taking data in 2029. And in the first 2 or 3 years, we will know what is the ordering of the neutrino and the absolute difference in masses. Just to give an order of the schedule of the experiment, now next year we will start construction. The cavern, as I said during the talk, have been excavated. This is the biggest underground laboratory of the world. And from next year, we will start producing the detector, which the components we produce all over the world will be shipped to South Dakota, will start going in underground. And it will take 4 years to complete. And then in 2029, 3 years, because then we take 1 year to fill the detector with liquid argon. And in 2029, we will switch on the detectors. So young students are the one which will deal with this detector. Since it will take data for
5 years
30
from now, right?
Yes,
5 years from
then,
now.
Yes, 5 years from now, and then it will take data for 30 years.
30 years, whoa.
Yeah.
That's something. Yeah, we are, and we think that our experiments in condensed matter, they take, when they go overnight, you complain because they take too long. Yeah. Any questions? If there are no questions, let me ask another question myself. When you were talking about the initial idea that there was a violation of conservation of energy, I recalled when Phil Anderson, P.W. Anderson, was visiting Niels Bohr, they wrote a paper together where to explain the beginning of their understanding of quantum mechanics, they proposed the violation of conservation of energy. So they even wrote a paper about that, saying that quantum mechanics violates conservation of energy, but then they retracted the paper later because they realized that, that quantum mechanics is crazy, but it doesn't do that. It doesn't violate conservation of energy. So that's just a thought that your comment about the violation of conservation of energy brought to me.
Yes, it was a very serious discussion that was at the time for what I was able to understand, and they took seriously into consideration the possibility that energy was not conserved, but is. There are many cases in the history of physics of this kind of crazy hypothesis, like the existence of the ether and so on.
Yeah.
And then takes years to go out of this kind of crisis. Typically, it's the experiment then put orders and these things.
Oh, yeah, exactly. Yeah, physics is done in the lab.
Yeah,
not
right.
in the mind of theoretical physicists. Edson, you have a question? Your microphone is off. Your microphone is off. Well, I'm not. I can. Edson, your microphone is off. We can't hear you. We can't hear you.
Hear me now? What about
okay.
Now?
Yeah,
okay.
yeah.
It was on, but for some reason was not captured properly. So thank you very much, Professor Ettore, for the nice talk. Now I'm not familiar with elementary particle either. George, I'm a condensed matter physicist. But I have been working with Majorana Fermi and condensed matter, which are not beast, it's not elementary particles, you know. But well, there's some discussion I read over the last 10 years, and well, some people think that neutrino could be a Majorana Fermi.
Right.
Can you elaborate on that a little bit?
Yeah. Well, this is part of this set of experiment which had the goal of measuring the mass of the neutrino. There is people think that neutrino could be a Majorana particle. That means that it coincides with this antiparticle. The particle and antiparticle are the same thing. If this is true, we should be able to observe a very rare decay that clearly is not been observed yet. That is the double beta decay without the emission of neutrinos. We know that the double beta decay exists. That is a simultaneous decay of two neutrons into protons with the emission of two neutrinos. This has been observed. There are some nuclei for which the simple the standard beta decay is energetically less convenient than the double beta decay. So in this case, you really observe the double beta decay simultaneous with the emission of two neutrinos. If the neutrino were the Majorana particle, that is, it coincides with is the same particle as in the antineutrino, that it can happen. It is possible a decay of double beta decay without the emission of the neutrinos. It's like if the two neutrinos annihilate, or better, if one neutrino emitted by one nucleus, by one nucleon is absorbed by the other. And so the decay happens without the emission of neutrino. But this can happen clearly only in the case the neutrino is a Majorana particle. So there are experiments since several years on looking for this decay. And these experiments are mainly installed in the Gran Sasso laboratory. I'm familiar with them since I worked there for several years, where they use substantially these nuclei, which are able to make double beta decay, which are germanium-76, tellurium-130, with different experimental techniques, and they are trying to observe this kind of decay. At the moment, it has not been observed, but there is the tendency of believing that neutrino can be a neutrino particle, and so there are experiments. This experiment will go on for 20 or 30 years to reach the sensitivity which is necessary to verify or discard completely the possibility that neutrino is a Majorana particle. So this is what you say is true, and is being investigated very extensively by the particle physics community.
Okay, so Edson, are you satisfied? Yeah, we can't hear you again. We can't hear you again. I don't know what's going on. Okay, there is a question here in the chat by Mardonio. Is the oscillation mechanism between changing neutrino types well understood?
Yeah, this is a mechanism that is well understood and well measured by several experiments along the year. And it culminated with the Nobel Prize of 2015 that was awarded to Art McDonald, Takashi Kajita. The parameters which define this oscillation are known. Not all of them are with precision. So we are entering now in the precision phase of neutrino physics, where these parameters are going to be measured with more precision at the level of below 10%. What is being investigated is the possibility of the existence of a fourth neutrino, because there have been some anomalies in neutrino experiment that cannot be explained by this three neutrino scheme. So the hypothesis is that exists a fourth neutrino which does not interact with anything. So it's called the sterile neutrino, because it has not been never detected. And there are experiments in LHC at CERN which define that the maximum number of neutrinos is 3. So we know that the active neutrinos are 3, but nothing prevents the existence of neutrinos which are not active. So this neutrino will be inactive, and the question is, so how can we know the existence of this fourth neutrino? Because it will participate in the oscillation mechanism. So instead of being a 3 neutrino oscillation mechanism, it will be a 4 neutrino oscillation mechanism. And this could change the oscillation pattern, especially at short distance. So you should see anomalies at short distance. This is exactly what has been observed, because we are trying to explain this anomaly. So there is a series of experiments at CERN, at the Fermilab, where the neutrino source and the detector are at less than 1 kilometer. There are 3 detectors in the space of 1 kilometer. There is one 100 meters, one at 600 meters, and one at 1 kilometer. That are studying the oscillation at short baseline, we call at short distance, to exclude the possibility of the existence of this fourth neutrino. Actually, the existence of fourth neutrino is disfavored by the result of this experiment. So the mechanism, we believe that the mechanism is 3 neutrinos. We understand pretty well how this is working. We don't know if neutrinos are violating the CP symmetry. This is something which we'll discover in the next years. And the parameters are known, but we will measure with precision again with this next generation experiments. So this is more or less the status of things.
Okay. I have a couple more questions, if you will. If you could show again your presentation and go to slide 24. I was a little bit curious because when you went through this slide, you said that these reactions are well understood, but I was wondering if the standard model cannot predict the mass of the neutrino, how can it predict so well these reactions? So
well, this is another standard
prediction. Okay.
This
so
is
that was my next question.
Yeah.
Okay.
This is the solar standard model. I said, in fact, this is a bit confusing. This is the model of the how the sun works, how the nuclear reaction inside the sun works, and this is pretty well. These rates are pretty well known. So the neutrino come from here.
Okay.
So this, yeah.
I assume that what you do is to do the measurements of these reactions, and then whatever energy is not accounted for, you say, okay, this energy is coming from neutrinos that are produced, and that's how you get
energy. Yes, the energy is taken into account, and in fact, this the modern experiment can well measure the energy of these neutrinos that comes from the sun. So you can substantially you measure the rate of each kind of neutrino coming for different reactions from the spectrum. You have the spectrum, which is the sum of all of them. Then you need to know very well the background, because these neutrinos have energy of few MeV, up to the maximum is 18 MeV, and so there is the experiment need to have very low background in terms of gamma contamination or neutrons and so on. So assuming that one can dominate the background, is able to decouple of this kind of neutrino from the global fit of the spectrum.
Okay. Okay. And my last question, let me see, there is no other questions here. My last question is the equation that you showed for the neutrino oscillation. It looks pretty much, when we teach a course on standard quantum mechanics 1, and you are studying a two-level system that has a perturbation.
Right.
This induces oscillations between the two levels. So is that something similar, or?
Yes.
So what is the perturbation?
It's exactly the same.
Okay.
The point is that the mass against autostate do not coincide with the Flavor autostates. So the story is so we have 3 mass eigenstate of the neutrinos, and the Flavor for a neutrino mu is a combination of the three autostate of mass. So when nuclear reaction produce neutrinos with the fixed Flavor, that is fixed type. For example, the decay pion produce a neutrino mu, which is a combination with 70% of neutrino type 1, 20% neutrino type 2 and 10% neutrino type 3 in terms of autostate of mass. The mass autostates are called Nu1, Nu2, Nu3. So, and these three autostates have slightly different masses. So, during the propagation, this is the effect of the interference between these mass autostates. So, which are slightly different masses, and so this exactly is the problem that you are saying, that is in a classical interference process of a quantum system.
Okay, okay, very, very, very interesting. So if we do not have more questions, we will thank the speaker again. Thank you very much. And I will be sending you an email asking for the slides so that we will post the slides together with the video in our YouTube channel, so that people can enjoy the talk and learn about the neutrinos all year round.
Okay, thank you a lot for the invitation. It was a pleasure. I hope that one day I can come there physically and we can meet.
Sure, sure. Yeah, we don't have, we are a small program here. We don't have anyone working on high energy physics, but it would be, I have very fond memories of UNICAMP. I did my undergrad, my master's, and my PhD there. I assume that you are in the Raios Cósmicos department?
Yes, yes.
So you are a colleague of André Koch Tavares, right?
I think he's retired, probably.
Oh, he retired. We did our undergrad together. So he was a very close friend.
Yeah, well, if you want to come here and visit us, so we have this lab which was renewed in the last few years. There are a lot of things happening on this Brazilian neutrino involvement. That there is a very big investment from Brazil in this sector.
Okay, yeah.
So, if also the students are interested, we are very happy.
We have many students watching this talk, so I hope they will get an interest on it.
Sorry.
No problem. So thank you very much, and
very well.
I hope we can meet sometime later.
Okay. Thank you a lot.
Okay. Bye.